Hello. Yeah, so it's already chapter 8. So we are finishing. We are near like 2/3 of the into the semester. So from chapter 8, we are going to change our topic. Like so, the style will be different. So from here, we will consider data, and uh, we uh, we will discuss how to estimate something that we would like to know. So it's quite different from what you have done up to now. So, and as you may expect, estimation is the main topic in any statistics. So, uh, like roughly speaking, you can understand that estimation is the ultimate purpose of statistics, right? So we are entering a very important chapter today. So let me start with a very, very general and abstract concept. So simply speaking, we need statistics because we cannot observe everything. If you observe everything, then you don't need statistics. You just need computation, right? But as you know, statistics is more than computation. Of course, computation is a part of important issue in statistics, but it's not everything. The main reason, as I said, so the statistics starts from the assumption that we cannot observe everything. We only observe a part, but from the part we would like to understand everything. That is a simple summary of what we do in statistics. And more rigorously and more academically, we call the everything as the population. So there are population of voters in an election. So imagine. So then, if you open all votes, then there is no statistics needed. Once the results is revealed, then it is not statistics anymore. But until all the votes are open, then you need to estimate who is going to be elected and what would be the difference, things like that. So population is everything you wish to observe but not possible. And on the other hand, the sample is what you observe, which is just a part of the population as you see here. So we would like to understand the blue, but we cannot observe all of them. Instead, we observe only this smaller, like orange circle. And from here, we'd like to extend some properties about the population. For example, before the election results are revealed, we have political surveys, polls, right? For example, you ask 1,000 voters about their a view or who they would vote for example, in a survey. So then they are just a part of the voters, all the voters, but still we can make some like educated guess about the result of the election. So that is statistics. Okay, so distinction between population and the sample is the most important uh, concept in statistics, because population is what we want to know, and sample is what we know, what we observe. Okay, and then their relationship is like this. So when you have population, from the population you sample your observation, your sample, like literally sampling is to generate a sample, random sample. That is when you move from population to sample. We discuss how the random sampling works in chapter 7, right? So random sampling is this arrow from population to sample. But in practice, that is purely theoretical, like a discussion, because we never observe population. Just mathematically, we assume there exists population, and we studied what happened if you randomly sample random sample of size n. Then we learned it's approximately normal distribution, mean does not change, variance decreases, blah blah blah. These kind of theoretical results we can connect the relationship like this. And in practice, what we are going is the other way. We have sample. From the sample, we would like to estimate the population. We would like to understand the population, right? So that is statistical inference. Random sampling theory was purely theoretical, purely mathematical derivation, but statistical inference involves real data and calculation, computation, right? How to utilize your information and how to simplify your computation, things like that. All these practical issues are in this direction. Given the sample, how can we understand, how can we guess something about, some characteristics about the population, right? As I said, for example, what percentage of voters would vote for a certain candidate based on your observed survey, right? Something like that is that's the statistical inference, which we are going to discuss through 3 chapters. Chapters 8, 9, 10 are about statistical inference. Okay, so again, think about that. Population is the larger, whole set, everything you would like to observe, but we can't. So we observe small part, which is sample, and from the population to sample is understood as the random sampling theory, and the other way, from the sample to the population, is inference. Inference is basically the statistical methods we are using in practice. And also, similar, maintaining that distinction between population and sample, we can think about two, counterparts, a few counterparts, to these population and sample. For example, we learned parameters. Parameters can be defined as some numerical measures about the population, right? So it describes how the population is distributed. Examples include mean, median, variance, probability, right? On the other hand, we have statistic. Statistic is also numerical measures, but it is calculated from the sample. That's the only difference. Statistic is calculated from the sample, but parameters are about the population. And examples also are the same. Statistic, you can think of mean, median, variance, probability. So, as I write here, the only difference between parameter and statistic is whether they are related to the population or the sample. It's a matter of how you calculate, or when you calculate them, what is the basis? It's population or sample. Okay, so this is the key difference. When you define parameter, conceptually you need infinite observations. Of course, it is not possible, but this is the easiest way to think about the difference between parameter and statistic. If you can calculate infinite observation, if you observe infinite number of observations, and if you calculate the mean based on them, then we have population mean, which is a parameter. But if you only have, say, 100 observations, or it doesn't matter, 1 billion observations, still it is finite. Even if a billion observations is a huge data, but still it's finite. So as long as it's finite, that is a sample. So it is a sample mean. If you calculate the mean from billion observations, still it cannot be a parameter. It is just statistic. Okay, then because they are based on different target or different pool, they have different properties. First, parameter is unknown. As I said, you need infinite number of observations. So it is not possible to calculate. You never observe infinite observations, or you cannot observe everything. If you do, then you don't need to. If you do observe everything, then you don't need to worry about statistics and then you don't need to define parameter. It's just simple, right? Matter of computation. So, endless within statistics, to study statistics, we have to assume that you do not know parameter. If you know this, it is not a problem. It is not a statistics problem. Okay, so because it is unknown, it becomes the target of our inference. We would like to know this guy. That's the parameter. And usually, we denote a parameter by theta. Greek letter theta is just kind of just generic parameter we would like to know. On the other hand, statistic is based on finite observations, so you can calculate that. So it is known. You have a number, tangible number for a statistic. But the problem with the statistic is random error. It is based on a random sample, so it follows the sampling distribution properties we learned in the earlier chapter. So it is random. It is not fixed. So it may be different from the true parameter. So that is based because of the random sampling error. So, but it is important because we do not know parameter, but we know the statistic. So we are going to use a statistic to estimate a parameter. That's the relationship between a parameter and a statistic. So for example, if you calculate, suppose that you want to know theta, but to guess theta, you use theta hat as an estimator. Then theta hat is a statistic. This must be calculated from the data. And by the way, we call this theta, and it's on top there is a hat, so we call this theta hat. That is also a generic notation for an estimator for theta. Okay, so understand, like, again, point is parameter is unknown, but it is constant. Statistic is known but random. That's the contrasting characteristics of these two objects. So let's think about then, and then when based on this same framework, there are two different types of inference methods. One is estimation and the other is hypothesis testing. Estimation is like this. Simply speaking, their difference is how you ask a question, whether it is yes or no question or open question. Like, for example, in estimation, it is like what percentage of voters support candidate A, or what is the mean gas price at gas stations in New York City. It is open question. I'm just asking you, and your answer should be just a number. Can be any number. But on the other hand, if you change your question like this, do more than 50% of voters support the candidate? And is the mean gas price in New York City lower than $3? For example, if you change your question in this way, yes or no type question, then the corresponding statistical inference is hypothesis testing. So simply speaking, you have a hypothesis. More than 50% support candidate A, or mean gas price lower than $3. So that's your hypothesis, and you are asking if that is correct or not. So that is called hypothesis testing. They are similar, related, but different. So we are going to discuss estimation methods in chapter 8 in this chapter. And hypothesis testing is more kind of exotic, so it's a little bit different from our typical estimation framework. So we will devote 2 chapters to learn hypothesis testing in chapters 9 and 10, right? So that's what we are going to have. And some examples of population and sample in a presidential election. So you'd like to predict the result before the election happens. That's exactly a statistical problem. In that case, the population is all voters, every voter who actually cast a vote. And the sample is survey respondents. So you do survey for a certain number of people, certain number of voters. And the parameter, I will simplify the parameter as the probability of voters supporting candidate A. And then the corresponding statistic is probability of respondents, like those you observe, respondents supporting candidate A. So as you can see, the structure probability is neutral. Probability doesn't mean whether it is population or sample, but like probability whether it is based on all voters or just from survey respondents. That's the key difference, right? How you calculate the probability will determine if it is a parameter or a statistic. Similarly, in gas price in New York City, population is all gas stations in New York City. If you could visit everywhere and record their prices, then that's what you want. But we cannot visit all gas stations, so we sample some of them. So observed gas stations in New York City is your sample. And the parameter is mean gas price of all gas stations in New York City, like if you could observe everything. But on the other hand, statistic is the mean gas price only from the observed gas stations. Again, mean, the average, is neutral. It can be used for population and the sample, but depending on how you calculate it, it could be a parameter or could be a statistic. Okay, so then think about another example. We would like to estimate the defect rate. So you manufacture batteries for a smartphone, for example, and you are worried about the defective batteries among your products. And you'd like to check how many are defect. So then if you view this as a statistical problem, what is not correct? Population, all batteries you produce, and sample is the batteries you inspect. Parameter is probability of defective batteries among all you produced. Statistic is probability of defective batteries among you inspected. And all of the above are correct. Think about this. Okay, the answer is E. All of them are correct. Okay, and here I'll give you another question. Excuse me, something is not. Yeah, sorry, I'm sorry about that. So parameter of interest is what we are going to estimate. So that is, we usually say the target of our estimator as the parameter of the interest. So we are interested in that parameter. Then think about this. What do you think is not a parameter? So first, standard deviation of life expectancy. B, expected increase in sales after a price cut. C, total number of heads when you toss 10 coins. D, difference in mean gas prices in New York and California. E, conditional probability of making a second free throw after making the first one. Think about what you cannot estimate. So the answer is C, right? So standard deviation, expectation, mean, conditional probability. These are well-defined parameters. As long as you imagine them, imagine they are calculated from infinite number of observations. So they are well-defined, but the problem is C. Number of heads is random. This can be different when you throw another time, right? So it cannot be your target, right? It is purely random variable, so it cannot be a parameter. So that is the first thing you have to understand. A parameter cannot be random, and you should be able to calculate that if you have infinite number of observations. So the total number of heads, if you set expected number of heads, then it would be different, but simply number of heads is not a parameter. Okay. So this was up to here. I just set up a basic framework for statistical inference, including estimation and hypothesis testing. From the next video, I'm going to explain estimation problems specifically. Okay. Thank you for watching, and see you in the next video.